Thank you so much, Mbali. Thank you so much for also the energy. Now, remember, we know you guys are going into revision week, so that's why we're here. So welcome to another beautiful Tuesday. Yes, you are with me, Utobile Nkosi, and thank you so much to Liberty. A big shout out to you guys for sponsoring the show. And remember, guys, if you want us to answer any of the questions that you guys have, remember to download the Tenfold education app, send through your questions, and we will answer it. Because it is revision week, we are answering each and any type of question that you guys might have. So we make sure that you guys are walking into the exam room fully ready. Now, remember to study smart and not hard. Remember, if you do not understand something, ask. You never want to find yourself sitting in the exam room stressing because you forgot to ask or you remember how it kind of goes. So make sure you guys are studying smart. It is critical, but you guys can definitely make it. So in today's show, we are doing a mixture of paper 1 and paper 2. And as always, I'm going to try to answer the question and also tell you what the examiner is looking for, how you should answer the question, and then where the question comes from, how it starts, and actually kind of teach you so that we go in depth with the question. The first question that I have is based on electrostatics. Now, I know in grade 12, we don't really do electrostatics. It is a grade 12 question, a grade 11 question, but in grade 12, they also bring in some grade 10. So let me take you guys back in history. In grade 10, when we did electrostatics, we had two spheres that touch and then move apart, and we know that charges or electrons were accepted and donated, and then the two spheres have a new charge, and we also could calculate the number of electrons that were actually transferred. In grade 11, we had an introduction of a point charge and the attraction or repulsion forces between two bodies, taking you back to Newton's law of gravity. Right? They'll tell us we have a point charge, we have a sphere and another sphere, and we must calculate the force between the two. In grade 12, we do it in 1 dimension and in 2 dimension. So you must make sure that your theorem of Pythagoras is on point. So the first question, it says a metal sphere, which is A, is suspended on a wooden beam by means of a non-conducting wire. Right? Remember, when we talk about non-conductors, they do not conduct electricity, and that is a string, and it has a charge of +6, and then it has a mute C. Now, something to also bring into this, in grade 10, we were taught how to convert. When we talk about charge, we talk about coulomb, right? And it must always be a C. Now, the examiners try to spice it up, and they can first give you as not a small c, definitely. They can say nanocoulomb, millicoulomb, picocoulomb, and so forth. You must always convert this to a C. So you need to know whether it's times 10 to the -6 and so forth. Unfortunately, you do not get that in your formula sheets, so it's something you must know by heart. So if you are still having a bit of issues with this, go back to your grade 10 book and then we can sort it out. So we have that metal sphere, it's suspended, and that is then the charge that the sphere has. So now 7.1.1 says, were electrons, were they added or were they removed from the sphere to obtain this charge? Assume that the sphere was initially neutral. Now, one way that I like explaining this is taking it from chemistry. When we have a neutral atom on the periodic table, we have an equal number of protons and an equal number of electrons, right? So electrons are negative and protons are positive. Equal means they cancel each other out. If we take carbon, for example, it's 12 electrons and 12 protons, 12 negative electrons and 12 positive protons. So a -12 and a +12 gives us 0. If this atom was to accept electrons, my number of electrons is going to increase. So from 12, I'll have 13, take another one, 14, 15, and so forth. I am more negative than positive, so my charge will be a negative. That is why when you look at the periodic table, like things like oxygen, nitrogen, they'll have -2, -3, and so forth because they are accepting extra electrons. In this case, when we have a positive charge, it means that electrons were taken away. Let's go back to the carbon. If we have carbon, it's got an equal number of electrons and protons. I give away my electrons. I give away 1, I give away 2, I give away 3. My electrons keep getting less and less, meaning I am more positive than negative. So a positive charge means my electrons were removed, and that is then why it is positive. So 7.1.1, we know that they were removed. And it's very important that you stick to what the examiner said. Here they said added or removed. So don't bring in any other types of wording, especially if they have it in capital letters. Then we have 7.1.2. It says calculate the number of electrons added or removed from the sphere. Now, for us to do that, we need some type of formula. This is a formula that we learn in grade 10, 7.1.2. We have a formula that is N is equal to Q over some use this, or some just write an E. So it doesn't really matter how you write it. It's the same. I'm going to keep it at E. Now remember, guys, in physical sciences, you do get a mark for writing the formula, because you are showing the examiner that you know what's going on. In some places, you don't get a mark for using the formula, but in most places, you do get a mark for doing so. Now, also remember, if you are using a formula, it guides you to see what do you have and what don't you have. For example, in the first one, we know we have a sphere. N represents the number of electrons. A capital Q represents charge. Now, they told us that the charge of this sphere is positive 6 microcoulomb, coulomb. Now, I know that for me to convert that, I'm going to say 6 times 10 to the negative 6. That is my conversion. If you move from that to coulomb, you times that by 10 to the negative 6, and your charge moves to coulomb. You have to do that. If you don't get the correct answer. Now, E is a constant. So every electron will have that charge, and we use 1.6 times 10 to the negative 19. Well, something nice about that is that you do get that in the formula sheet. However, you need to know that that represents an electron, the charge of an electron. Now, I know in your formula sheet it is a negative 1.6 times 10 to the negative 19, but you can use it as a positive. You will not get penalized if you use it as a negative. So let's see the number of electrons that we're going to have. Now, it's just mathematics. We're going to put this in our calculator. As I always say to you guys, put everything in brackets. It makes it so much more easier. To the exponent 6, bring that down, and that is over 1.6 times 10 to the exponent negative 19. Bring that down. Let's see the number of electrons. So I've got 3.75. Remember, always to 2 decimal places, times 10 to the negative 13. I'm going to have 3.75 times 10 to the 13. What did they ask us? Electrons. You must always remember, when you're answering a question in physics, it's almost like having an SI unit. When you talk about weight, you must have kilograms somewhere there so that the examiner knows what you're talking about. When we talk about vectors and scalars, you must have direction to show the magnitude as well as the direction. So remember, if they ask you number of electrons, end off your answer by electrons. You are showing the examiner that you know we were looking for electrons, and the answer that you got actually proves what we were looking for. So always keep that in mind. So now we've calculated the number of electrons there, and that was for 3 marks. So that was an easy 3 marks, but you have to know this from grade 10. So 7.2, we've got point charges, which is Q1, Q2, and Q3. Another important thing, when you are naming your charges, whether in an electric field or a magnetic field, make sure that you always keep to the naming that they have. And I'm going to show you how. So these charges are arranged at the corners of a right-angled triangle. The minute you see right-angled triangle, you go dun 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 dun. Theorem of Pythagoras must ring somewhere in your head, as shown in the diagram below. So this is the diagram that I have. I've got Q3 here at the bottom. It has its charge. Now already I can see that all my charges are not converted. Remember, to move to mute to coulomb, I must times that by 10 to the negative 6. Do not forget. Something that I am looking or picking up in this diagram is that R and R is exactly the same, right? And remember, R means the distance between their centers. So I know that the distance I'm going to find here is going to be equal to the distance in this direction. I also see that this makes an angle of 45, and I see my right-angled triangle there. Another clue that they've given us northwest, east, and south. So always remember, if they put this in your equation or question, always remember to always keep to the direction that they've used. I just want to take you back. When we were doing momentum and the question said a car moves to the east and another car moves to the west, we stuck to east and west as a direction, and we didn't bring in left or right. If the question was talking about left or right, then we stick with that. Let's follow the same steps here. They've given us northwest, east, and south. Let's stick to that. So then it continues to say, we just move down. It continues to say that the charges on Q1 and Q2 is a positive 2 and a negative 2. So we can see the charges are equal, just in the opposite direction, and that's respectively, and the magnitude of Q3 is 6. The distance between Q1 and Q3 is r. We've already established that. The distance between Q2 and Q3 is also r. That we've already established. The charge on Q3 experiences a resultant electrostatic force, right? That is F, an electrostatic force of 0.12 newtons to the west. So now let's see what's happening. I just want to take this off. It's to the west. What does this side say? To the west will then be in that direction. I can see that this is a positive, but it is going into that direction. Remember, we are talking about electrostatics. There is either a force of attraction or a force of repulsion. Opposite charges will attract and like charges will repel. For an example, if we have a positive charge and another positive charge, they will repel. If we have a positive charge with a negative charge, then they want to attract to each other. So always keep that in mind. Now we can already see that Q3 is moving to the west, and this is a positive 2. So we need to know that something is going to be asked regarding that. 7.2.1, it says, without calculation, identify the sign, whether it being positive or negative on Q3. So now, remember, when we talk about electrostatics, it's charges. If this is a positive and Q3 is being attracted to Q1, it means that Q3 must then be a negative, because if it was like charges, it would have repelled. So then that means it would then be a negative. Let's answer that question. So that is 7.2.1. It means that it is a negative. They did say without calculation. How do I know this is a negative? Because I know from my data, my information, or my knowledge on electrostatics, opposite charges will attract and like charges will repel. Just want to take you further a little bit. In grade 10, this is the first thing that we drew. If we have a positive and another positive, they will repel. If we have a positive or negative and a positive, then they will attract. So if it's moving towards the negative, it means they are attracting with each other. So let's see, 7.2.2 says draw a vector diagram. Now remember, when we talk about vectors in physics, we're talking about it must show the direction in which the force is moving, right? Just by mere looking at the diagram, we should be able to see which force is what and in what direction it's moving. Taking you back a little bit, when we did work, energy, and power, we draw free body diagrams. We had to use vectors to show in what direction the object is moving. Was there an applied force? Was there frictional force? And so forth. By looking at the diagram, we were able to say or tell what is actually going on. The same thing must be done with electrostatics. However, the only difference here is that we have a force of attraction and a force of repulsion. How I always teach my kids, always put your point at what is going to be affected, and then think about if this one comes along, is it going to attract or is it going to repel? And that is then how you draw your vector diagram. So let's look at this question. Just go down here. So draw a vector diagram to show the electrostatic force acting on Q3 due to Q1 and Q2. So if I've got Q3 on this side, and I know that this is a negative, it's also negative, opposite charges, like charges, will repel. So I know that this one is definitely going to move away from that one because it's going to repel. But Q3, if this is a negative and this is a positive, it definitely wants to attract, right? So it's going to move. Now I need to draw that vector diagram and then name my forces. You always put your point at the charge that is being affected and in what direction is it going to move if the other one comes along. So that is 7.2.2 vector diagram. A point, we are talking about Q3. Show the examiner you know what's going on. In this direction, it will be the force of the second one on the third one. In this direction, Q3 is going to be attracted from the first force and the third one. So that is then my vector diagram for Q3 on what is going to happen there. 7.2.3 says write down an expression. Now remember, if they say write down an expression, they're not saying calculate everything. Already we know that we have the distances that are unknown. So an expression means something must be, is going to be missing there. It's just an expression, and the expression is going to help us calculate what we're looking for. I want to take you back. When we did forces, when we did Newton's when we were mixing Newton's first, second, and third law, and we were talking about tension and so forth, and we had to do simultaneous equations. We were making expressions and then doing simultaneous equations. So we're doing exactly the same thing here, only in electrostatics. I hope you guys can already see the trend where we're actually using the same forms of mathematics and principles of physics to answer different questions. So let's write down my expression first. So my expression, I know in terms of the horizontal components of the electrostatic force, I know my formula for my electrostatic force, and this is Q3 by Q1. So it means I am only dealing with these two here. I'm dealing with Q1 and Q3. At the back of my mind, I know that the distance here will be exactly the same as the distance there. So let's write down our expression. So that is 7.2.3. Remember, electrostatic force is F is equal to K, Q1, Q2. Always start with a formula. It always makes the perfect sense. We're looking for the force that one will have on Q3. Remember that my K is a constant, that is 9 times 10 to the exponent 9. You do get that on your formula sheet, so you don't have to stress. The charge on, let me just make sure which one is what, so I don't lie. The charge on Q1 is 2 and on Q3 is 6. Remember, we need to convert it. So I'm going to have 2 times 10 to the negative 6 for Q1 and 6 times 10 to the negative 6 for Q3. Remember, we do not have the distance, which is squared, and we also have it at an angle of cos 45. Always remember your angle. I'm going to put that there. This is r squared. I'm going to work out the top part. I still have F1, F3. Let's work out what we have there at the top. Let's see what we have. So I'm just going to put everything in my calculator, 9 times 10 to the exponent 9. Bring that down. Always put your things in bracket, 2 times 10 to the exponent negative 6, because if you don't put it in brackets, your calculator is going to do its own BODMAS. 6 times 10 to the exponent negative 6. Bring that down. I get that. But remember, I still have cos of 35, so that's multiplied by cos of 45. And then I get 0.076. Now I'm going to leave it to 3 decimal places because this is not my final answer. So I'm just going to leave it to 3 decimal places so that I'm more rounded off. 0.0764. If this was my final answer, I would have rounded it off to 2 decimal places. I still have r squared there at the top. So this is my expression. Exactly like when we did tension and all that stuff, I don't know. I have an unknown there, and I also don't know the electrostatic force. So that is my expression of how I can actually answer this question. The next question says I must then calculate R, which now makes it kind of easy when you're actually using your expression. Now that I have my expression, it means I can then use it twice. Let me write everything again so that everyone knows what I'm doing. 7.2.3, I am going to use a different color. So remember, if you're looking for f of x, they told us that the electrostatic force experienced by Q was 0.12. I know that if I find the electrostatic force on Q1 on Q3, I can add it to the electrostatic force that Q2 will have on Q3. I know that f of x, I can break up. Remember, this is my expression. I do know that the two distances are the same, so I can write this twice. So I've got 0.0764 all over r squared plus, because the distances are the same, I can write it like this, 764 all over r squared. Now it's just pure mathematics. F of x, the magnitude, just going to go back so you see where I'm getting that. The magnitude experienced by Q, the charge experienced by the resultant electrostatic force is 0.12. Remember, the word magnitude just means size in physics, so it's just a fancy word science teachers like using, so don't get confused. I'm going to use that twice, so I do know that the resultant is 0.12. There is 2 of this, so I can write it as 2, 0.0764 all over r squared. Now it's just mathematics. I'm going to multiply the top parts together. So I can just take that, multiply that by 2. I get 0.15. I'm going to write it to 27. So I'm going to have 0.12 on this side. I'm going to have 0.15 to, let's make it to 8. Let's round it off. And I'm going to have r squared. Now I must just cross multiply. Now it's just mathematics. I'm going to put this over 1, multiply this by 1, multiply that by r squared. On this side, I'm going to have 0.1528 multiplied. So I'm going to have 0.12 multiplied by r squared gives me 0.12 r squared. I want my r squared by itself. I divide both sides by 1.2. This and this will cancel. I'm going to have my r squared. Let me calculate what I have there. Let me take that. Let's just divide it by 0.12. Let's see what we get. I get 1.2727 going on. So I can say 1.2727 ongoing. Now remember, I'm looking for r alone, so I'm going to put both under a square root. This and this will cancel. I'm left with r. Let's see what the value or the distance is. I'm going to take that, put my answer in a square root, and then I get 1.128. I'm going to leave it to 2 decimal places, so the 8 will round off the 3, the 2 to then a 3. So my distance will be 1.13. And remember, when we talk about distance between the centers in physics, we talk about a m. We measure distance in meters. So the only tricky thing about this was to remember that because the distances are the same, I can write the same expression twice. Let's look at our next question. The next question that I have, we've calculated r. Now we have another question that says the magnitude of the electric field. Now, my darlings, most of you guys confuse the electrostatic force with the electric field, right? The formulas are not the same, right? When we talk about electric field, we talk about a point charge. So make sure that you understand the different formulas. You do get both in the formula sheet, but you need to know where you use what. So the magnitude of the electric field is 100 nanocoulomb to the exponent -1 at a point which is 0.6 meters away from a point charge of Q. 7.3.1 says, define the term electric field at a point in words. Now this we already learned from grade 10 and grade 11, so we need to know the definition. That's why it's not really for a lot of marks. But remember, if you have to define a term in physics, the words do not change. Most memorandums have maybe 3 to 4 options of how you can answer it, but there are certain words that the examiner is looking for, right? Without those words, you do get penalized. Remember, they are not saying explain what is an electric field at a point, they're saying define it. So if you go anywhere in the world, the definition must remain the same. If you open any textbook, the definition must remain the same. If you are explaining something, it's based on your own discretion. I can ask Mbali and say, Mbali, what do you understand by an electric field? And Mbali can tell me, no, Tops, it's when this and this happens. It's what she understands. But a definition of an electric field at a certain point must always be the same. So let's define that. And that is 7.3.1, electric field at the point. I know it is a long one. Do not take shortcuts. And do not write slang. An electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So this is what we have. That is our definition. Let's see what our question is asking us. So the question says, calculate the distance from point charge Q at which the magnitude of this electric field is 50 n dot c to the -1. So already I know that when we talk about electric field, my formula is E is equal to K Q over R squared. They want me to calculate the distance where the magnitude, remember that's just size, the magnitude of the electric field is 50. So they want us, they've given us this one, they want the distance, but I don't know the charge. I can go to my previous information. I've got the electric field, I've got the distance, so I must first find the charge of whatever they're talking about. Once I find the charge, I can then find the magnitude of that charge when the electric field is 50, nc to the exponent 1, and then I can find the distance. It is for 5 marks, so in my head, I can already see two calculations. So I must first find the charge because it's unknown. I know the electric field and I know the distance, but they want me to find the distance when that point charge is then when the electric field is 50. They want me to find that distance. So two equations. So let's calculate that. So this is 7.3.2. So formula first, K Q over R squared. They are telling me that my electric field is 100. Remember, K is a constant, which is 9 times 10 to the 9. I don't know this charge, but I do know that it's 0.6, remember, to square meters away, right? I must first find Q. So now it's just mathematics. I'm going to put this over a 1. I'm going to cross multiply. On this side, I'm going to have 9 times 10 to the exponent 9. I still have Q. Other side of my equation sign, I'm going to have 0.6 squared multiplied by 100. I want Q by itself because I'm looking for charge. I divide both sides by 9 times 10 to the negative 9. Some of you guys make silly mistakes and you forget to actually divide on both sides. Remember, if you buy a Father's Day present, you must buy a Mother's Day present. What you do on the one side, you must do on the other side. Now let's calculate this and see what we get. At the top, I've got 0.6. and that is squared. Remember to multiply that by 100. At the bottom, also in brackets, is 9 times 10 to the exponent 9. Close that. Let's see what I get there. So I get a very, very, very small number. Let's see how many times I can move my zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can say 4 times 10 to the exponent negative 9, and that is the value of my charge. So 4 times 10 to the negative 9 coulombs. But now that's not what the question asked me. They're asking me, we want to know the distance when it's 50, when the electric field is 50. So I know that E is equal to KQ all over R squared. Now I know that this point charge has now an electric field of 50. Remember that K is a constant, which is 9 times 10 to the exponent 9. I just calculated my charge. Now, just something to tell you guys. If for some weird reason you didn't get the charge here, which I hope you do get, make sure that you take the exact value that you got and then place it in to the next equation. You are showing the examiner that even though I did make a slight mistake, you can get credited for using your answer in the correct place. You are showing the examiner that you understood you first had to find the charge and use that charge amount into the new equation. So don't go think something else and then place it. You will get a mark for that. So the charge that I just calculated was 4 times 10 to the negative 9. But now they want me to find my distance. Remember, mathematics, cross multiply. On this side, I'm going to have 9 times 10 to the exponent 9. My charge is 4 times 10 to the negative 9. On this side, I'm going to have 50. And I still have R squared. I want R squared by itself. I divide both sides by 50. This side will cancel. I'm going to have R squared. Let's see what I get in there. I'm just going to put it exactly as it is in my calculator. And let's see what we get. So at the top, I've got 9 times 10 to the exponent 9. Bring that down. My charge, let me just backspace there. To the exponent 9, take it down. My charge that I calculated was 4 times 10 to the exponent negative 9. At the bottom, I know it is divided by 50. Let's see what I get. I get 0.72. So I get 0.72 on this side. However, I'm not looking for R squared. I am only looking for R. I put both under square root. What you do on the one side, you do on the other side. I'm going to take my answer exactly as it is and put it under square root. I get 0.84. The 8 is greater than 5. It will change the 4 into a 5. Always round off your answer to 2 decimal places. I get 0.85. When we measure distance in physics, we use meters, and that is in how we measure our distance. So that is our last question, I presume. I think, let me see. That was our last question. Yes, and all of this was for 21 marks. It does look complicated, but it really isn't. It mixes a lot of things, but it really is easy marks. So I think let's go for an ad break, and then when we come back, let's see if we can't do something in chemistry.